let's talk about Wien Bridge oscillators. In this video, we're going to cover a tiny bit of theory and math. We're going to do lots of simulation. We're going to build intuition, actually build the circuit, and of course, take measurements. So when I talk about Wien Bridge oscillators, I often give a quiz to students. What was Hewlett-Packard's first product? And it turns out it was this widget called the Model 200A audio signal generator. And it was based on Bill Hewlett's master's thesis at Stanford University. So here's a little photograph of the device and a truncated schematic and a couple of the specifications here. It had a 1 watt output and distortion of better than 1% over most of the audio range, and powered by just a standard line voltage. So what was this thing originally used for? And in addition to things like testing out telephone amplifiers and audio circuits, one of the first applications was actually in the production of Disney's Fantasia movie. So just a little snippet of history from hewlettpackardhistory.com. And I'll put links to every link that I go to here, I'll put in the I will put in the description. And then if I look notch down on this page here, we see a copy of the original schematic. So I don't know, I think that's pretty cool. So this is the original schematic of the Hewlett-Packard's first product from 1939. I actually took a tour of Stanford University a couple of weeks ago for my kiddo, and they actually have a replica of Hewlett-Packard's garage. So in Silicon Valley, the common origin story, every cool company has to start in a garage, and that comes from Hewlett-Packard. And I'm not sure exactly what model this is, but they've got one of the early oscillators sitting in here. Not sure if it works or not. Okay, so you can get a copy, or you can peruse a copy of Bill Hewlett's master's thesis. Again, I'll put a link in the description. And this is pretty wild. So this is a copy of Bill Hewlett's thesis. And let's take a quick little perusal through here, a bunch of text and a bunch of sort of circuit theory. We're going to dig into this a little bit further on and actually simulate this circuit. And what else do we have here? Okay, so this is one of the things that we'll be exploring in detail. The fact that an incandescent light bulb's resistance changes with the amount of current that you push through it, or really how much power is being dissipated in the filament. So we're going to explore that in quite a bit of detail. And here's where our light bulb shows up in our gain stabilization network. And I guess that's all we'll say about this thesis. Again, except that it is available and pretty cool piece of history here. Okay, so what about modern applications of Wien Bridge oscillators? Are these things still useful at all? So modern audio oscillators, the sound cards in your computers and phones and stuff, are actually pretty darn good. So the need for a pure analog oscillator is diminished versus times past. But this is an application note from 2011 on fidelity testing for A to D converters. So Linear Tech makes several families of very high performance SAR A to D converters with sub part per million. Yeah, so with distortion on the order of a couple of parts per million here. So testing these things is a challenge. And so the way we test these converters here, and I guess I like this little phrase here, to meaningfully test 18-bit A to D converters, the oscillator must have transcendently low levels of impurity, and these characteristics must be verified by independent means. So in block diagram here, the device that we're testing is this A to D converter, and the way we do that is we take a transcendently pure oscillator, put it through a pure gain stage, and see what actually comes out on the other end. And so we're actually going to explore this very circuit here, this very high purity oscillator, and what we get out of this thing if we look at sending the output of this oscillator through an A to D converter, we end up with a distortion of 109 decibels, so an extremely low distortion converter. Again, there are audio delta sigmas that do better than this, but this is a SAR converter, so 1,000,000 samples per second at 108 dB distortion is pretty wild. Okay. And then, so, the heart of the Wien Bridge oscillator is a bridge, a Wien Bridge. But what came before a Wien Bridge? And the answer is a Wheatstone Bridge. So Wheatstone Bridge is a very common circuit that you'll often study in your first semester of electrical engineering. And it's basically 4 resistors in a diamond. And what we do is we place a voltage across the top and bottom of this electrical bridge here. And then let's say that some physical phenomenon like temperature or pressure or torque causes one or more of these resistors to change. I can measure the difference between points D and B here on the circuit and get an actual signal out of this. And we have a simulation of that up on our analog devices in the Analog Devices Inc. Education Tools repository here. And so running simulations as you are studying your equations is really a great way of sort of building intuition and understanding as you're going along. So go through the math, but then play with some actual values in simulation. And so let's do that here. So here I've set up a basic Wheatstone bridge with 4. Actually skew this purposely to start, so I'm going to set this to 10K ohms. So notice here I've got 10K, 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 and just intuitively, if I have 10 volts between points A and B, and I've got equal value resistors, I get 5 volts out point C, and I also get 5 points out D. And a handy little trick in LT Spice is to take a voltage-controlled voltage source here with a gain of exactly 1. I can use that to sort of probe the difference between 2 points within a circuit. And so if I run this circuit, this is a DC simulation, then I notice that sure enough, the voltage at point A is 10 volts, the voltage at point C is 5, point D is 5, and the difference is 0 volts. So this voltage VCD is 0 volts. Now let's see what happens if I change this from 10K to 10.01 here, and then these guys will bump these guys up a little bit. 0.01 and 0.01. Okay, now let's run the simulation. Okay, so intuitively, I've dropped resistor 3, I've increased resistor 4, so D is going to go, the voltage at D will increase a little bit, and I have increased R1 and decreased R2, so C will go down. And sure enough, VC is 4.995, VD is 5.005, and the difference is 10 millivolts. Okay, so what that means is I can now take this 10 millivolts and I can apply it to an amplifier and measure the output of this physical phenomenon here. Okay, so that's all we'll look at. That's all we'll do with resistive bridges here, because this isn't very exciting. These are all DC voltages, and we are making oscillators. Okay, so what comes after a Wheatstone bridge? And the answer here is the Wien Bridge. And if I look at a Wien Bridge circuit, it's very similar, right? I've got 2 resistors, but in the other leg, I've got a resistor in parallel with the capacitor and a resistor in series with the capacitor. And here's where things get interesting. So we'll head back over to LT Spice, and here is our Wien Bridge. And instead of a DC voltage across the bridge, I've got an AC voltage. So I've set this up in LT Spice for AC analysis, and I give it an amplitude of 1.0 volts. That makes our math easy. And I've got some, somewhat arbitrary values in here of 10K and 10 nanofarads, 10K, 10 nanofarads. And I've chosen these resistors for a reason, this 20K and 10K. This is a divide by 3 circuit, right? So if I have 1 volt wiggling at A, I get 1/3 of a volt wiggling at D, and just like before, I can measure the difference. So let's run this simulation. And here I'm running an AC simulation from 100 hertz to 10 kilohertz. And let's run. Let's see what we get. So let's probe point D. Not very exciting, right? I get -9 dB, which is equivalent to 1/3, but let's probe point C. Look at that. So with point C, we notice at low frequencies, I have quite a bit of attenuation, minus 24 dB, and at minus 24 dB at 100 hertz, and then up at 10 kilohertz, I'm at, minus whatever this translates to, about minus 15 dB. But what is up with this point here? So if I probe right around 1.5 kilohertz or so, I have a peak. And if I see what happens, notice that the peak is exactly the same as that resistive divider, right? So I've got I have a point where the output there's a frequency at which point C and point D are equivalent. And I can get a sharp picture of that by probing the difference between C and D. And if I probe that here, notice I get this really sharp null. So at a certain frequency, the bridge is balanced, and I can force balance with an operational amplifier circuit. But let's look at one more notable characteristic of this plot here. So I'm going to get rid of the VCD. Let's cut out of here. Okay, so let's look at what happens with the phase of the output of the Wien Bridge here. So if I am exciting point A and I look at point C, again, this blue trace here, we've already looked at the gain. So at this magic point, the gain is a third. But what about the phase, right? So the dotted trace here is phase, which is noted on the right-hand vertical axis here. And what I notice is at that magic frequency, my phase is exactly 0. So if I have, let's say, a sine wave with a certain phase at A, I get exactly a sine wave out of C, attenuated by a factor of 3, but with 0 phase. A little bit lower frequency, my phase is a little positive. A little bit beyond, my phase is slightly negative. Okay, so this is going to be important in the next piece of our analysis, which is how do we get this thing to oscillate? And it turns out in order to build an oscillator, you need to meet the Barkhausen criterion, or Barkhausen stability criterion. So this is the properties of a feedback circuit that is sort of the boundary between an amplifier and an oscillator. And I'm not going to dig too much into the description, but I just want to point out the two criterion, or the two criterion for this boundary. And the first one is that the loop gain is equal to unity, right? So a loop gain of exactly 1. And then the phase shift around the loop is 0 or an integer multiple of 2 pi. So going back to our circuit here, we know that the gain of the Wien Bridge, the gain of the resistive capacitive arm of the Wien Bridge is a third. So that sort of indicates that if I need a unity gain, I need a gain of 3 somewhere in the equation. And then a phase shift of 2 pi. Okay, well, I have phase in, I've got phase out, and sure enough, 0 times 2 pi is 0, which is the phase shift that we noted at that magic frequency. Okay, so let's go back to LT Spice, and let's take this circuit and wrap a little bit of gain around it. So we'll close out of here, nope, and then let's open up the Wien Bridge VCVS gain circuit. Okay, so here I've got that Wien Bridge, but I don't have I'm not exciting it with a sine wave because I want this circuit to produce a sine wave. That's what we're after all. And so what I've got here is whatever my output voltage is. Again, this is a voltage controlled voltage source. So whatever voltage shows up at the input of this circuit, I multiply it in this case by 3.00 to get the output. And so let's see. So what I've done is, and then this voltage source here is a little kick because no circuit will start up on its own, or I should say no perfect circuit will start up on its own. Real circuits, there's always a little bit of noise or a little bit of offset that will start them up, at least if we're lucky. But in this case, I've got a theoretically perfect circuit and I have to kickstart it into operation. Okay, so we know that at some magic frequency, whatever wiggle I see at the output is attenuated by a factor of 3. So let's multiply it by a factor of 3 to get back to unity. And let's run this dude and see what happens. Okay, so let's probe the output. Wow, look at that. I've got an oscillator. Okay. So if I kick this voltage, and let's probe the kick voltage to see exactly what's going on here, right? So the kick voltage starts out at, yeah, okay, so the kick voltage starts out at some positive voltage. And again, the reason I do this is because I want my oscillations to be around 0 or centered around ground. And yeah, how cool is that, right? I kick this circuit once and it just sits here and oscillates forever. Wow, that's pretty neat. So how am I going to make this circuit? Okay, so I'm going to go over to my favorite electronic distributor. I'm going to buy perfect 10K resistors and perfect 10 nanofarad caps and put this all together, and it's magically going to work, right? Well, not quite. So let's say that, oh, and I also buy a perfect gain of 3 amplifier. But let's say that my gain of 3 amplifier, let's say that I order my gain of 3 amplifier, but it's not actually 3. It's you know, it's a 0.01% accurate amplifier, and I happen to buy one that is a little bit on the low side. So 2.99, gain of 2.99. Okay, so that's a real amplifier with some tolerance to it. Oh, look at what happens. Okay, so this isn't so, that's not such a hot idea, right? So my real amplifier, even if it's, you know, even if I get right up to 2.99, let's add another 9. So if I've gone and I've bought a more accurate gain of 3 amplifier. Oh, look at that. And the gain is still petering out. Eventually, my oscillations are going to stop. Darn. Well, what happens if we go in the other direction? Let's say I get an amplifier that's a little bit on the high side, 3.01. Okay, and wow, look at that. Okay, so when I kickstart this circuit, it starts off, it should anyway, look pretty good. Yeah, it starts off looking pretty good. I've got some oscillations going, but look what happens. They get bigger and bigger and bigger, zoom to fit. And eventually, my oscillator output is 30,000 volts. Okay, so hey, this is a great circuit. I can power my whole house. I can power an electric car in it, can't I? Well, you know, not really. You never get something for nothing. You've got to put energy into the circuit. And of course, eventually you're going to reach the limitation of your physical devices here. But conceptually, this circuit or this simulation allows you to explore that boundary between oscillation and no oscillation. So let's go back to perfectly meeting that Barkhausen criterion of a net loop gain of exactly unity, a net loop phase of exactly 0 or 2 pi or 4 pi, etc. And yeah, so I can play around with my theoretically perfect oscillator. So how do we take this theoretically perfect oscillator and make something that'll actually work in real life? So we're going to take a trip out to some of the active learning exercises on the formerly on the Analog Devices Wiki. We are in the process of translating these over to GitHub Docs. It's a little bit nicer of a presentation here, but we actually have a whole exercise on Wien Bridge oscillators. And towards the end of this, we see a practical implementation of a circuit we can build with real components here. And what you'll notice is I've got an amplifier, I've got this Wien Bridge network, I've got some gain setting components, and sort of the key to making this thing work are these anti-parallel diodes here. The way this circuit works is you'll notice that I've got the output of the amplifier is feeding this Wien Bridge network here, and the center of the network goes to the amplifier's non-inverting input. And I've also set up the amplifier for a gain of, just visually here, I've got about 10, 15-ish K in the feedback network, and I've got about 5-ish K in the input resistance here. And this 2K resistor is actually a potentiometer, so that allows me to tweak things to compensate for differences in gain here. So sort of intuitively, what you'll see is I've got a non-inverting gain of 3-ish, and then when I get above a certain voltage, these diodes kick in and effectively reduce the value of R2 to some degree, so it drops the gain down. And, you know, again, it's easy to say this in words, but let's head over to simulation and, again, get an intuitive sense of how this thing works. So we can close out of our perfect oscillator, because from here on out, we are based in reality. Let's see, so Wien Bridge oscillator complete. Okay, great. So here is the actual simulation from that screenshot. And let's see. Well, let's just run it first. So we'll go run. And it looks like, let's probe the output here. Hey, great. So we've got some oscillation here. And let's see. So this actually looks pretty good. This looks fairly sinusoidal. Okay, you can see the simulation steps in here, but let's see what the distortion is, right? Because if I clip the peaks off of a sine wave, then I know it's going to have some distortion components. And let's actually accentuate that and try to see what that looks like in reality. So I'm going to take R5 and I'm going to bump the gain up high by changing this to like 1 ohm. Okay, now let's run it. Okay, here, now we can actually see that the peaks are clipped off. Okay, so again, we'll clip off the peaks here. So that is not a very nice sine wave. So now let's go the other direction. Instead of 2K, let's put in 3K, right? So we're going to drop the gain. And look at that. Just like before, I get an initial oscillation, but then it very quickly dies out. Okay, so let's interpolate and see if we can find just about right. So 2K, I know, let's try 1.8K. Okay, I know that is, yeah, so that's going to oscillate. Okay, and then let's see, any visual? Yeah, so here again, I've got visual clipping here. Let's actually quantify that distortion here. So in LT-Spice, you can go View FFT. And I'm going to take the FFT, the Fourier transform of V out, and let's run this. And here's my output spectrum. So here's my fundamental tone is at about 10 dB plus 10 dB with respect to volt. Yeah, probably. Yeah, so it's 10 dB with respect to volts. And if I look down in the lower left-hand corner, let's move this down so we can see a little bit better. This is about, yeah, so it's about 1.5 kilohertz. And then at 4.4 kilohertz, so this is the third harmonic, I get a tone, the fifth harmonic, and so on. And if we want to quantify that, I can measure the difference between the two. Wow, that's only 15 dB distortion, right? So that's not a very good, that's not a very good sine wave. Okay, so let's get a little bit better here. So we'll go and again, we know that 2K, oh, sorry, that was 1.8 ohms. Okay, well, that actually accentuates our experiment, so that's good. So let's go back to 2K, which we know oscillates. And now let's take the FFT. Oh, I also want to take this initial startup out of my FFT. So the way I'm going to do that is I'm going to start saving time at, let's call it 25 milliseconds, 0.025. Okay, great. So now now when I start up, my FFT is only going to consider the waveform after my startup transient has died out. Okay, so let's go in here, view FFT again, the out. Okay. All right, so now let's look at the distortion components here. If I look at the delta, that's about 27 dB. Okay, so better than, we can do the math in our head. So 20 dB is 10% distortion, 27 dB, yeah, that's 7 dB better. So we're getting there. Now let's reduce the gain a little tiny bit more. We'll go 2.1 and then run again. Okay, and then view FFT. Okay, and all right, so now if I look at the delta, I'm at about, oh, still 27 dB. Okay, so maybe we are approaching the limitations of this circuit here. I'm going to try one more try here. So let's go 2.1. Let's really interpolate. Let's go 2.3K. Still oscillates. Okay, maybe we'll get there because in practice, I know we can get to about 1% distortion in practice. Okay, so we're getting closer. Now let's look at FFT. Okay. All right, so look at that. So here we're at about 36 dB distortion. Okay, so again, let's zoom to fit. We'll look at our first couple of components here. Again, if I start here, that's oh, and a thing to notice, when I was clipping hard, the amplitude was about 10 dBV. Here I'm at about 3 dBV. So my overall amplitude has reduced, but that second harmonic distortion is now down 36 dB. So I'm approaching 1% distortion. Hey, look, I can start a big multi-billion-dollar company with my 1% distortion oscillator here. Okay, let's get just a tiny bit better. 2.4, 2.5K. Oh, notice that I'm still starting up. So I am right on the edge of this thing not oscillating. Okay, and then here, if I look at the delta, my third harmonic is down 38 dB. Okay, so my circuit is just barely starting up, and I'm at 30, yeah, so 38 dB distortion. And, you know, let's, on a whim, let's try one other thing here. I'm going to set my horizontal axis to linear so that we can sort of see our harmonic profile a little bit better here. So our fundamentals at 1, the first noticeable harmonic is at about 4. So that's the third harmonic. Why is my second so low here? And let's do a little bit of Fourier theory here. Remember that a sine wave that is symmetrically clipped only produces odd harmonics, and that's what we're seeing here. So again, 1.5 is present, but 3 kilohertz is down pretty far. Let's do an interesting little side experiment here. We're going to take one of these diodes and let's make it a Schottky diode. Okay, so a BAT54 is a small signal Schottky diode. Okay, and what does that do? What that does is when the output swings high in the high direction, I get a forward drop of a silicon diode worth of voltage drop. In the reverse direction, I have a slightly lower voltage. Remember, a Schottky diode has a lower forward voltage drop. So now let's run and see if that accentuates our second harmonic. Okay, so again, there's a little segue here. But let's see if we get something interesting out of this. Okay, let's view FFT V out. Okay, and then we'll go linear axis to make things easier to see. And sure enough, look at that. So here's 1.5 kilohertz, 3 kilohertz, right? So asymmetrical clipping causes my second and I get a little bit of fourth and a little bit of sixth here, but that second harmonic really pops up when I asymmetrically clip. And then vice versa, let's do the same thing. Pick new diode. If I make this guy a Schottky diode again, okay, I expect my third harmonic to be pretty terrible, but I bet that second harmonic disappears. Okay, so let's run this again with 2 Schottky diodes. And now view FFT. Yes, please. Linear axis. Okay, and let's see what happens. Okay, so here's 1.5, 3 kilohertz is absent, and 4.7 is present. So again, this is the fundamental. Second harmonic is almost absent, and third harmonic pops up again because now I am back to symmetrically clipping. This is an awful lot of talk, and we said that we would build an oscillator here. So let's take a look at what we're going to build. Okay, so in the exercise, the lab exercise talks about building the circuit up on a breadboard. This picture here, this is my first attempt at building this thing on a little breadboard here. So I've got an op amp, I've got a potentiometer to tweak the gain, and I actually have a couple of different capacitor selections so that I can sweep the frequency over a broad range. I like this circuit so much that I built up a little circuit board here. And we'll dig into some of the other circuitry here, but this board supports both the anti-parallel diode clamp for controlling gain, but I also wanted to support a circuit that's shown in application note 43 that actually uses a little light bulb for gain control. So let's take a little break from simulation and staring at app notes and actually build this darn thing. Okay, so let's begin our assembly. So oftentimes I find that the hardest components to install are the little jumpers and headers and things. So I'm going to show you a little trick that I picked up a couple of years ago. And what that is you take a spare board and you put some standoffs on the board upside down, and then you install, or you sort of place the jumpers upside down in this board. Okay, so we're going to do the same thing for all the jumpers that we need. So there's a couple here, one here. We need a 4-position jumper here, another 4-position jumper here, one there, and let's see, I think that is all of our jumpers. I'm cheating a little bit and I'm looking at a fully assembled one here. Okay, so if I look upside down, yeah, so we've got these guys. Oh, this is not a jumper. Okay, good thing I checked. All right, okay, that's it. Okay, so what we're going to do now is we're going to take our other board and let's see. Oh, these guys were long pins down. Long pins down. And same thing here. Nobody's perfect. Okay, great. So now it should be fairly easy to line these guys up. Perfect. And then these are ready for soldering. Okay, great. So that should be all set. And if we pop this off, look at that. A nice perfect soldering job. Everything's nice and even and straight. Okay, great. So then the next thing that you do is, let's see, I guess you can either use little standoffs to hold things up. You know, I'm going to do that just to make other parts of this a little bit easier. Okay, so there's the jig. I can put that away. All right, so this gives us a nice surface. I prefer soldering resistors and leaded components from the top sometime. So let's get some of our other components in here. All right, so I've got my components laid out here, ready to rock and roll here. So I'm going to sort of keep these over to the side and I'll talk you through it. All right, so we've got some 25 ohm resistors. So I'm going to bend these leads, and just so that they don't touch the desk, I'm going to clip these as I go along. And let's see, it looks like that is R1 and R2. And you don't really have to be this picky about it, but I try to keep these guys in the same direction so you can sort of read the color code here. Okay, and then we've got 1K resistors. So these are our frequency setting resistors, or the maximum frequency setting resistors here. And so we'll go 1K over here. All right, and let's see, let's just keep going. We'll get our diodes in there. Okay, great. And then this may horrify some viewers, but I just find it so much easier to solder things from the top primarily and then reflow from the bottom because I'm picky like that. All right, and then let's get our potentiometers in. Okay, so this is should be a 1K potentiometer, and yeah, if we get it just right, 102. Okay, so that is our light bulb gain setting potentiometer. Okay, and these are sort of tallish components, which gives us an advantage. We can flip the board over here. So let's see, that's 502. Yep, get that in there. So that's a 5K pot. And we're going to get this little guy in here. Okay, and then I'm just going to kind of wing it here. So let's see if we can set this guy down. Yep, good deal. And then what I like to do is tack one wire down. Okay, and then lift the board up, press from behind, give it a little reflow. Same on the other pot, give it a little reflow. Okay, great. Now you know that they're flush and you can hit the other leads. And while we're at it, let's do a reflow and a trim break. So we're going to reflow, reflow. Okay, looking good. All right, what's next? I guess we can put down our range setting capacitors. Okay, and you notice that I used a footprint where you can I wanted to make this conducive to junk box builds. So I put in sort of multiple footprints here. And even here, I'm gonna go and I'm gonna actually bend the leads a little bit to hold them in. And let's see, so that's all our caps. Okay, and like the potentiometers, I'm gonna pull that trick where I'm gonna solder one lead and then get it flush, just to be picky. All right, and so the footprint for the potentiometer here is kind of nested. And the reason for that is when I first did the prototype here, I was looking through DigiKey and I found these potentiometers, which are really nice. They're kind of cute and compact. They're also $9 a piece, which is fine if you're building one board, but if you're building 10, that starts to eat into your budget. So I nested another footprint for a much cheaper dual 10K potentiometer. So let's install that guy. Let's see, that's the tallest component on our board, so I'm going to put this one in last. I lied. Okay, so next up is our socket for our op amp here, and again, using a little trick, I'm going to hold it with one hand and solder one pin. Okay, great. And then same trick, we're going to press and push. Don't burn your finger on the other side. Okay, next let's solder in our 327 gain control incandescent bulbs here. All right, so that is just a plain old light bulb with and I laid out the footprint here so you could put, again, junk box light bulbs or wire it out to a remote bulb of some sort if you wanted to. Okay, so okay, let's see. We are nearing the end. You know what? Let's just be complete. I'm going to solder in our little external clips, just in case you want to hook on an external power supply. So press those guys in. They should friction fit. Great. And then we're gonna goober these guys up with solder. Home stretch. I'm also going to put in, I left spots here for some larger electrolytic capacitors. So usually these little guys are enough to keep the op amp from oscillating, but you know what? Let's put some bulk bypass out here. So let's get our potentiometer in here, tallest item on the board. Just right, okay. And then that should hold itself in, but I'm going to tack one down from the top anyway. Hey, that's everything. We'll install the op amp later, but let's just do a little clip. Okay, wonderful. Let's install our op amp, and let's set our jumpers for the middle frequency range. And we will set ourselves for diode clamp amplitude control to start. You know what the next step is? Power check. Okay, we are ready for a power up check here. So I have connected the Wien Bridge oscillator to my AD-ALM 2000, which we will call the M2K from here on out. I've got the positive supply, 2 ground wires, and negative supply hooked up to the headers here. And then the channel 1 of the oscilloscope input is connected to the output here. I've got the range capacitor set to the center 0.1 microfarad, and I've selected the diode clamp gain control method here. Okay, so in Scopy, next step is we'll go over in Scopy here, and let's start at the home screen. So I've connected to my M2K, and I'm going to go first to the power supply, and we can dedock these things as well. So I'll get my power supply out here. And I want to set to the maximum of plus 5 volts and minus 5 volts. And let's enable both of these, which we can do at the same time here. Okay, great. So here's our power supply is all set. We'll get rid of this for now. And then let's go over to our oscilloscope. And sure enough, that looks like a sine wave, doesn't it? And I can adjust the frequency. And it looks like my trigger point is way off to the side here. Yeah, there we go. Okay, so I've got a trigger set up, and let's drop our voltage a little bit. Okay, great. So I can change my frequency, and I can adjust the gain of the circuit here, the diode clamp gain here. But you know, this is just pictures on the screen here. Let's get a sense of what this thing actually sounds like. So I've got this is actually a 50 ohm speaker, so it's a relatively high impedance, but it's kind of nice for testing a circuit like this because it doesn't load as much as an 8 ohm speaker. And there it goes. And I think you should be able to hear this. Wow, how cool is that? Holding it up to my headset. Okay, let's check out our other frequency range. Oh, wow, okay. And on up. How freaking cool is that? Okay, so we know it works and we can hear it working. All right, and from now on, we're going to take off the speaker just because we don't want to annoy ourselves too much here. Okay, great. So let's take a look at the scope shot a little bit here in a little more detail, and I'll make this a bit bigger here. What do we notice? Well, we notice that we are visibly clipping a little bit, and I'm going to set us back into the center range so that we can get a frequency of about 1 kilohertz. Okay, so I've got the measurement feature turned on here. Let's see, yeah, measurements. Yeah, so I can enable measurements of the sine wave here. Okay, great. So you notice I've got a frequency of 146 hertz, peak-to-peak value of about 6 volts here. I've got some visible distortion in here, which is not unexpected. You know, again, we've got that diode clamp in there, so we expect that at low gains where that diode is not coming into play, we should have a nice pretty sine wave, and as we increase the gain, those diodes start to kick in. Okay, let's get our frequency up to about 500 hertz, and that makes it easy to mentally calculate things like distortion, where our distortion components ought to live. Okay, so we've got a fundamental frequency of about 500 hertz. Okay, now I'm going to mess with the gain a little bit here, and let's notice what happens. Okay, see how the bottom is clipping first? That's kind of intentional. I've actually soldered that Schottky diode in parallel with the silicon diodes that are soldered into the board here. So I wanted to play around with those different harmonic components here. And then just to get a measurement on that, I've got my handy little Harbor Freight meter here. Let's measure the forward drop of a plain old silicon diode. Okay, so we put the positive, let's get one diode out here. Yes, these are my 40148s on the anode and then on the cathode. And we get about 0.6 volts on the forward drop on the diode with whatever test current this meter sends through. And then I found in my box O diodes some BAT54s. So these are Schottky diodes. And if I measure the forward drop of this guy, it's about 300 or 250 millivolts, so considerably lower. And also, just for fun, I didn't solder this in, but another alternative would have been to use a germanium diode. So I've got a bag of germanium diodes here, and similarly, these guys have a considerably smaller forward drop than a silicon diode. Yeah, so about 360 millivolts, so somewhere in between. Okay, so let's take some measurements with this setup here. Get these guys out of the way. Okay, so we'll go over to, we're gonna stop looking at the screen here because humans are not very good at detecting distortion components in a sine wave like this. But you know what is good at that? Is the Fourier transform. Okay, so this is the spectrum analyzer feature of Scopy here. So it's just taking data just like the oscilloscope, but instead of displaying in the time domain, we're displaying in the frequency domain. And we can move the cursors around here. Sure enough, we've got about 500 hertz. And just like we saw in simulation, I've got a component at 1,000 hertz, and then 1,500, and then 2,000. So there's our fourth harmonic, fifth harmonic, sixth harmonic, and so on. And then let's get an idea of what our THD, our distortion, is. And I don't think this, yeah, so it looks like this isn't measuring. Yes, this doesn't do a direct measurement of distortion, but that's okay. We can just sort of mentally see how far down we are. So here we're at about -18 and about -47. So gosh, I'm going to need a calculator for that. So our second harmonic is down. Let's see, so we got -18. Let's see, -18.8. And then we're going to subtract from that. Looks like these are about equal, about 47. Minus -47. Okay, so that's about 30 dB distortion. And then let's reduce the gain here and see if, we know that our fundamental gain is going to drop, but let's see if our harmonics drop faster than our fundamental. Yeah, boy, that pesky Schottky diode is really being a pain here. Okay, so I wanted to do this. I have not practiced this, so let's see what happens when I clip out that Schottky diode. Okay, so let's make sure, so our gain is high enough to sustain oscillation. Let's clip out that Schottky diode. Wow, look at that. I've clipped the wire and the second harmonic just disappeared here. Okay, great. So now let's drop our amplitude. And let's see if I can get, yeah, so here we're just at the edge of oscillation. Okay, our noise floor is down about 90, and as we just bump the gain up a little bit here, let's see if we can hit 40 dB distortion. So I'm going to come over, let's set our, here, so now we've got 10 dB per division. There's 10, 20, 30, 40, 50, about 60 dB. So this is actually not bad. But if I go over to the oscilloscope and run this, the amplitude's not that high. It's only about 1.5 volts peak to peak here. So again, we have this huge trade-off between amplitude and distortion. So we'll go back over to the spectrum analyzer. Yeah, so as soon as I get up to, gosh, let's get a voltage here. So as soon as I get up to like 4 volts peak to peak, if we go over to the spectrum analyzer, here we've got 10, 20, about 30 dB distortion if we are lucky. Okay, but still, that's usable in some situations here. Now, we said before that the original Wien Bridge oscillator used a light bulb for gain control, and I've actually got I have a light bulb in here. But you know what? Before we dig too much, before we actually flip over to light bulb mode, let's take a look into why that light bulb works as a gain control element. Okay, so what is it about a light bulb that we're after here? So this is a light bulb that I'm using here. This is a number 327, just a sort of a pilot lamp for electrical control panels. And this is actually a 28 volt bulb, or it's rated for 28 volts. But our circuit is only running on ±5, so clearly we're not using it for its ability to shine. So let's go ahead and measure what happens as I power up a light bulb. So I bought these from DigiKey, and I bought a couple of different versions of them just because. But what I've got here is I have one of these light bulbs connected to an adjustable power supply, and I'm measuring both the voltage and the current through the power supply or through the light bulb. So let's ramp it up to its operating voltage of 28 volts. 28 volts. There we go. So at 28 volts, I have about 40 milliamps of current flowing through this thing, and it's glowing quite brightly. Let's just do some mental math here. So I've got 28 and 40. Let me drop the voltage down to 14 and see if we get 20 milliamps. Okay, no, so at 14 we get 26 milliamps. So we actually have more current than we're expecting. So more current means the resistance is lower. So as I increase the voltage across the light bulb, increase the current, its resistance actually drops off. And it's easier to see in a plot than for me to describe in words. So I went ahead and took a bunch of data at a bunch of different voltages here. So 1 volt, 2 volt, 3 volt, 4, 5, 10, 15, and 20. And then let's come over to Excel and plot out and see what happens here. So what you'll notice is that, yeah, just like I said, so at low currents or low voltages and hence low power dissipation, the resistance is lower. So this is voltage versus current. So the slope of this line is conductance. The inverse of the slope is resistance. So I've got a high conductance, low resistance, followed by low conductance, high resistance here. Okay, and that is the magic characteristic of this bulb. So where that bulb is in the circuit, if the voltage increases, we want the gain to decrease. Okay, so this was a plot here. And of course, like we said before, building intuition or simulation is a wonderful way to build intuition. And you guessed it, we are going to simulate a light bulb, or we're going to run a simulation of the behavior of a light bulb. So this transient thermal model, I found digging around through some old example LT-SPICE files. I can't find the original author. If I do ever find the author, I have to thank him or her because this has really come in handy. And let's see what we're doing here. We've got a lamp, so we've a lamp modeled as a resistance, but we are modifying the resistance based on its power dissipation. So if I look here, I've got this is normalized temperature rise, and the current through this source here is proportional to the power being dissipated in the lamp. I then drive that into an RC circuit here that this is a model of the thermal resistance to the outside world. So this will take some staring at to get down to a fundamental understanding, but we're just going to run it a couple of times here, and you can run this on your own. Okay, so and then what I'm putting across this light bulb is a ramp function. So I start out at 0 volts. I go up to 20 volts because our model starts to break down much above that. I've got a rise time of 50 seconds and a fall time of 50 seconds and a period of 100 seconds. And if I run this, well, it's up in the plot here. Here's what I get. So sure enough, at 2 volts, I get a certain current. At 14 volts, I have about 30 milliamps or so. 36 milliamps or so. So not exactly what we measured on the bench here. So clearly I could tweak this model a little bit, but the fundamental characteristic is there. You notice that I'm running the simulation very slowly, right? So I've got a 50-second period here. And the reason is the circuit relies on the thermal time constant, right? If my gain is changing as the output of my oscillator is moving up and down, all this does is generate distortion, lots of it. So I'm actually relying on the fact that the lamp takes a little bit of time to heat up and cool down. So I'm going to go and I'm going to change this. I'm going to drop this by a factor of 10. So instead of a 50-second rise time, 5.0, 5.0 fall time, and a 10.0 period. Okay. And notice I start to have a little bit of spreading here, right? So my model, my light bulb heats up and then it cools down, and I can see that things are starting to take a little bit of time. And then and again, this is still very, very slow relative to the 1 kilohertz oscillator that we have here. So now let's go and drop from 5 seconds to half a second, 0.5, 0.5, okay, and a 1 second period. Okay, and now we see things spreading down. So I clearly have a different trajectory as my light bulb is heating up versus cooling down. We can actually measure this on the bench. And the way we're going to do that is by taking this theoretical model with ideal voltage sources, and we're going to put it in a curve tracer circuit. Okay, so I've got that same thermal model of the lamp, except I've wrapped a practical circuit around this thing. And what I mean by that is I want the ability to use a function generator to ramp the voltage up and down, and I want to be able to measure the current in a practical way. So what I've done here is I've taken the lamp and I've put a 10 ohm current sense resistor in the ground path, and I have an operational amplifier circuit here, a little op-amp circuit with a transistor to boost the output current capability. And I can hook this up to my AD-ALM2000, my M2K. I can use the waveform generator to ramp the voltage up and down. I can use one of the oscilloscope's inputs to measure the lamp and to measure the voltage across the lamp, and the other to measure this current sense resistor. And notice here that the voltage drop across this resistor, I'm not actually measuring that. I take that out of the equation using the differential inputs of the M2K. So let's run our simulation just to make sure that in theory our circuit should work. Yeah, here we go. So I am measuring the current through R1, and I am plotting the voltage of A with respect to B. Right. So in theory, I should be able to build this circuit up and measure it with Scopy and my M2K. All right, and yeah, you guessed it. I have built the circuit up already. I kind of designed it as I was building it, so I'm not going to go through the whole build process here. But you see, I've got a little socket so I can swap out the lamp here. I've got an op amp, and I've got a cable to my M2K. So I'm going to take a little break and set this up. Okay, so here we have our little curve tracer circuit. We've got a 28 volt, or I guess I have it set to 30 volt power supply coming in. I've got my AD-ALM2000 waveform generator output going to the input of the amplifier, and I've got my channel 2 across the current sense resistor and channel 1 across the light bulb itself. So if we come over here to Scopy, I've set up the signal generator for a triangle wave, and notice that I've got a fairly low frequency, so 2 hertz or 2 cycles per second with a 5 volt amplitude. So basically we're going to gain that 5 volts up to 25 volts through the amplifier. And let's see, the oscilloscope is set up. I've got channel 1 and channel 2 connected, but I've also got XY mode enabled. So let's cross our fingers and start the function generator. Is that working? Okay, there we go. All right, you see the light blinking? Sorry, this is just too amusing here. So not only do we have the light blinking over here, but if we look in Scopy, wow, how cool is that? I see that same characteristic that we were measuring in LT Spice. And I'm not going to go through the math here. This is qualitative at the moment here. Of course, whatever voltage I measure on that sense resistor, multiply by 10 to get the current, because it's a 10 ohm current sense resistor. You can see that my signal generator is railing out. That's the op amp hitting the stops here. So let's drop the amplitude and let's see if we can explore the different operating points along this curve here. So remember, the light bulb doesn't care whether it's AC or DC. The power is power. So whatever the RMS voltage across the light bulb is, whether it's the sine wave output from your signal generator or this trace, It's the RMS voltage that determines the power dissipation. So I'm going to drop the amplitude. So there's 1 volt. So now we should be exercising a little bit of a, yeah, so we're exercising 1 point along this curve here. So let's drop the power dissipation. I'm going to drop the offset. And let's see if we can visualize this thing operating at a lower dissipation, hence lower resistance. Okay, so we've got 500 millivolt offset, 1 volt peak to peak. Okay, look at that. Our curve is up and down. And actually we can, let's bump the frequency as well. So more indicative of what the circuit's going to be doing in reality. Okay, so there's 20 hertz, and notice that I can't see anything happening on the light anymore. And we can actually speed this up. Let's speed up the time base a little bit as well. So let's go 50. This will make things happen a little faster, a little more responsive. Oh, did I do that? Yes, that's in the right direction. Okay, great. So now let's go and play around with that offset. So up 1.5 volts, 2.5 volts, 3 volts. Okay, and notice the slope is flattening out, so my resistance is increasing. And notice that you can, I don't know if you can see this or not, but the light is flickering just a little bit, but we can see the filament up here. So yeah, so this is where it's at. So as I increase the average, as I increase the continuous dissipation in the bulb, my resistance increases, my conductance is, yeah, resistance increases, conductance, or the slope of this line is lower. Okay, so yeah, so please build the circuit up, run the simulations, and try to really get a deep understanding of what's going on here. And I think we are ready to switch our Wien Bridge oscillator over to light bulb control mode. Okay, before we switch over to light bulb gain control mode, let's just remind ourselves where we were as far as performance was concerned. So here I am set to a 1 kilohertz fundamental, and if I adjust the diode gain down a little bit, look at that. I can get the distortion down a bit, but boy, it's just on the edge of not oscillating. Okay, so here I can tweak, and boy, that, you see what I mean? It's just not really that stable. So yes, I can get it to work, but if I want decent distortion, 10, 20, 30, 40, 50 dB distortion, I really have to work at it, and it's quite touchy. Furthermore, because of component imperfections and mismatch in the 2 stages of this dual potentiometer here, if I change the frequency, then I have to adjust the gain a little bit as well, right? So see, I tried to go up in frequency, and here I have to retweak the gain every time I change frequency. And if I want reliable oscillation, then I have to bump the gain so high that my third harmonic pops up quite a bit. So 10, 20, 30, yeah, so about 40 dB or 1% distortion here. Okay, now let's switch over to light bulb gain control mode. So I'm going to take out these 2 jumpers and pop them in their locations here. Okay, and look at that. So yes, I've got harmonics, but look how far down they are. First of all, my fundamental is a lot higher. So I'm at about minus 3 dB, 10, 20, 30, 40, 50, 55-ish dB distortion here. And then let's back the gain off a little bit. Okay, a little bit more. Okay, yeah, and so let's see what we have here. So 10, 20, 30, 40, 50, at least 60 dB. So we're at about 0.1% distortion, so at least 10 times better. Okay, and then let's play around with this a little bit. I'm going to bump the gain a little higher. Yeah, and see, it's, again, it's not that sensitive. And then let's try adjusting the frequency down, back down to a kilohertz. Wow, look at that. Okay, so 10, 20, 30, 40, 50, 60 dB distortion here. And then let's play with the gain a little bit. see if we can get it down. Again, trading off gain and distortion. Okay, so yeah, so we're approaching the point where we have to start questioning things here, right? So I'm measuring the distortion with this AD-ALM 2000 box here. What is this box's inherent distortion? Okay, so let's go over and try to get some insight into that. So this is a web page that is on a reference manual for the M2K's internals. And if I scroll down a little bit, I hit the analog front end. So the analog to digital / D to A converter is this AD9963. It's actually intended for communication applications. So it's not really the highest performance device in the world, at least at low frequencies. But again, it's in terms of size and cost, it was perfect for the AD-ALM 2000. I've also got other distortion mechanisms in here. So the analog input that comes into an attenuator and goes through a couple of analog switches and a bunch of amplifiers, each of which are going to add their own distortion. And if we look at the A to D converter itself, so this is the data sheet. I guess we're on page, well, here, we'll come back down here. So this is the data sheet for the AD9961/63. And if we look at the RX ADC, so this is the ADC specifications, it doesn't have an awful lot about distortion, but if I look at spurious free dynamic range, so this is usually one of the harmonics is going to dominate, 70 dB typical. So again, not even guaranteed, but as we start getting into the 70s, we need to start questioning our AD-ALM 2000 itself. Okay, so where do we go from here? Is there something that I can, like, how can I get a little bit more confidence in my distortion measurement? Well, you know what is not a bad option here is an external sound card. So this is my SoundBlaster G6 external sound card, and this actually has some pretty nice specs. So let's take a look at that. Okay, so this is the SoundBlaster G6. And so here's a nice little picture here, flashy marketing document. And if I scroll down to specifications, it's a little bit light on specs. It says audio quality 130 dB SNR. I think this actually refers to the D to A converter. The A to D converter is not very well spec'd at all, at least on the marketing page here. Turns out somebody has gone through the effort of taking some independent measurements here, apparently with the Pink Panther as a mascot, and they've gone through and taken some data on this thing, D to A to D converter, and at some point, I think this focuses on the DAC, and then at some point we get down, ADC audio measurements. Okay, usually I'm too lazy to go this far into testing. And what we notice on the ADC testing, again, I don't know exactly what this person did, but we see THD plus noise about 0.01%. Okay, so 1% is 60 dB. 0.1% is 60 dB. 0.01% is about 80 dB. Okay, so even with this measurement here, we have some sense that this sound card might be able to do the job. And I found some teardowns of this thing, some pictures inside here, and I asked ChatGPT what A to D converter is used in this thing. Again, people seem to focus on the DAC for some reason, and here's a picture of the ADC. I think I have cracked it open before, and I'm pretty sure it is this device here, the Cirrus Logic CS5361. And if we look at THD plus noise is 105 dB. Okay, so again, this is distortion plus noise is 105. They don't break out distortion separately, but this tells us that, we can probably get maybe 105 a little bit better in terms of a distortion measurement. And I am going to take a little break and see if I can set that up next. Okay, let's remind ourselves of where we are here. I've made some minor adjustments here. I am now at 2 kilohertz fundamental, and we'll see why that is in a minute. And I go over to the spectrum analyzer and I refresh my memory that we do have cursors, horizontal and vertical here. So I am measuring the difference between the peak of the fundamental and the Sorry, that is, yeah, so that's the second harmonic. Again, we're down, we do have second harmonic present, so asymmetrical clipping, but it's considerably farther down than with that Schottky diode. So here our delta is about 58 dB. So, you know, again, 0.1% distortion. We were getting a little bit better earlier. But again, we are approaching now the limits of the AD-ALM 2000. Okay, so I want to get a baseline here. So now I'm going to take my SoundBlaster and I am going to disconnect the M2K entirely. And the reason is I don't want any extra ground loops going on between my SoundBlaster and the card. I've switched over to a floating power supply here. So this is a floating low noise 12 volt power supply. And this is just a little attenuator board. So I'm going to plug in the SoundBlaster. And then how are we going to talk to that thing? And the answer is with a little Python script. Okay, so I have recently found a number of really handy utilities out there for using sound cards. So it turns out there's a library called, well, SoundCard, obviously. And let's take a quick trip out to the internet. Yeah, so here is a SoundCard library for use with Python, pip install SoundCard. This one, there's a number out there, but this one is particularly easy to use. And of course, it's documented with examples and things like that. So let's go over and so we use SoundCard. And then for the analysis, we're using Generalizer. And Generalizer is an open source project that Analog Devices has put together. I've talked about it in a previous video here, but it's basically a library for generating and analyzing data converter applications or data converters in general. And so just to give you a quick little tour here, a sound card equals blaster. So when there's multiple sound devices on most computers and you can identify it using a subset of its description string. And I set up a microphone. So my mic equals sound card get microphones. And here's where I pull some data, right? So data equals my mic.record. I set my sample rate to 96 kilosamples per second, and I take 96 kilosamples, so 1 second worth of data. This was just a little test function for playing a tone that I was playing with earlier. A little bit of data manipulation here. I do a little bit of a hack here. The numbers that come back are floating point, and Generalizer is expecting integer data. So I scale everything to 24-bit word, and then slice out a few data points at the front and put up some plots for us to look at. And then finally, I send the data to Generalizer, and I'll leave it up to you to dig into this. I will throw this up on GitHub for whoever is interested in running it. And let's just run this thing and see what happens. So we'll run. Okay, great. And I have a plot in the other screen here. So that actually doesn't look very nice. And what I'm finding is that occasionally we'll get dropped samples, and I don't see any warnings about dropped samples or drop frames here. So let me just run this again. Okay, that was interesting. What I'm finding is that there appears to be some interaction with all of these USB devices I have attached to my computer here as I'm shooting this video. So I've got a sound card, I've got a camera. What else? The AD-ALM 2000 itself, and yeah, so I kept getting that weird spreading, like I was dropping data points here or there. So when I stopped recording and reran this test again, here I get exactly what I'm expecting. So yeah, so in the FFT here, I see my fundamental, I see my second and third harmonic, and they're right about the same place they were with Scopy. So yeah, it appears that Scopy is not doing such a bad job here. And then let's see, here's the sine wave. Oh yeah, so let's look at the calculated results. I've got a THD of 53. Yeah, you know, again, I think I could get a little bit better if I ran this a couple more times here. Okay, but I'm not going to beat that too much further. What I am going to do is take one more reality check of this setup, and I'm going to do that with this guy here. So this is one of those Jim Williams oscillators built into a box. This is from that application note we noted earlier, the demo circuit 1858. It's a very low noise Wien Bridge oscillator. And yeah, you can go through the documentation on that one afterwards here. So I'm going to disconnect our little Wien Bridge oscillator. And once again, just a little attenuator board here, and plug this guy in. And I'm going to run this, and I am expecting some spreading. I'll pause it and then take another shot afterwards if it doesn't work out. Yeah, so I'm going to keep getting spreading here. So I'm going to pause this, take a shot, and be right back. Okay, now we're talking. All right, so you'll notice that this spectrum is an awful lot cleaner. I've got my fundamental down, down, maybe 7, 8 dB here, but look at that second harmonic is down better than 90 dB. And, again, the human eye cannot perceive that level of distortion in a time domain plot. And then if we look at the calculated numbers here, I've got THD of 88 and SNR of 80. And again, I expect that this box is considerably better than that. I also expect that I could do better if I did a better job of wiring this with a more solid ground plane. A USB isolator may help as well. There's a couple of other mitigating techniques that we could use here. Okay, but yeah, here we've got a really nice, interesting experiment where we built up an oscillator, took some measurements with the M2K, compared it against a SoundBlaster, and finally against a very low noise, very low distortion external oscillator as a benchmark. The next step would be to take this into the office where I have a Stanford Research SR1, which is sort of our benchmark for very low distortion and low noise measurements. Okay, so I'm going to do one more experiment. So I'm going to take a little break and be right back because I want to show you one more neat thing before we wrap it up. Okay, so I'm back to using the M2K to measure my output here. And remember, the resistance change of the light bulb is due to the temperature of the filament. And so we should be able to hit it with a blowtorch and hit it with some freezy spray and see some difference in amplitude. So I'm going to zoom in on the amplitude of the fundamental here. Okay, so we're sitting here at about -3 dB. We'll put a cursor there just for fun, so make it a little bit easier to see. And then if I hit with freeze spray, we notice that we see a little increase in amplitude. And then if I warm it back up again with the torchy, okay, again. So what that means is it takes less amplitude to maintain the filament at a given temperature. And that is where we're going to wrap it up. I hope you found this interesting. Again, all of the design files for this board are up on GitHub. I'll put together a DigiKey shopping list for this thing as well. And yeah, until next time, we'll see you.